Okay, good morning, good evening, good afternoon, depending on where you're joining us in the world. Welcome to the MechE Alliance seminar series, our weekly connection to what's happening on campus with our faculty, with our students, and with our external partners. Today is my great pleasure to introduce Professor Vivishek Sudhir, who's in MIT's Mechanical Engineering Department, working on quantum measurements and control. His work is centered around measurement techniques of mechanical oscillators for big stuff and small stuff, kilogram scale test masses to gravitational waves, and using precision control to test fundamental theories. His talk today is the birth and death of the single quantum of vibration. So please hold your questions to the end or ask them in chat, but we won't ask Vivishek questions until the very end. I'll marshal them and we'll turn it over now to Vivishek and hear about his exciting work in quantums of vibration. Vivishek, all yours.
Yeah. Thanks, Brian, and thanks, Teresa, for having me here. It's nice to talk to you, and thanks everybody for coming up. So let me start by sharing my screen and making sure all of that works. Let's see. I just want to bring up the laser pointer too. Okay, that should work. Yep. So let's go. Yeah, so I wanted to talk to you today about some recent work that we've done in collaboration with some of my friends at EPFL in Switzerland, Santiago and Chris, both of whom I've had long collaborations with. And the work was recently published in Physical Review X. After the talk, you might consider reading that paper to get more details. But I want to talk about, observing the birth and death of a single quantum of vibration. And what I mean by a vibration is in the language of, phonons. So what is a phonon? I just want to give you a brief idea of what a phonon is. So if you think of a model material as, just a collection of point atoms, let's say, there are two kinds of atoms, one of mass m1 and another of mass m2, slightly different, and there's lattice spacing A. This simple material is just a linear chain of these two kinds of atoms sort of, stuck together by Hookean springs. And you ask, what are the normal modes of this infinitely long chain? This is a standard calculation in, material science and solid state physics. You would actually see that in fact there are two kinds of normal modes, two families of normal modes. One called an acoustic branch and one called an optical branch. And I'll clarify what these names are. So what you see here on the x-axis is just the momentum of these normal modes, and on the y-axis is their frequency. So this is really like a dispersion relation, right? So here, you see the familiar linear dispersion relation that says, the frequency is just proportional to the wave vector. That's, your standard, frequency is inversely proportional to wavelength kind of relation that you know from sound waves and that sort of thing. So the acoustic branch really, at least in this regime, is essentially what leads to the propagation of sound in most materials. And the optical branch, on the other hand, is a higher frequency kind of excitation. And if you look at the picture of how these vibrations happen, the acoustic branch basically has all their atoms moving in phase, whereas the optical branch has these phonons moving out of phase. So that's certainly a mechanism that vibrates at a smaller length scale and therefore a higher frequency, a higher energy, and so on and so forth. So that gives you an intuition for why there are these two branches. And as I said, the theory of conventional elasticity, continuum elasticity, is really just an effective continuum description of this acoustic branch, where you don't really, your theory does not really have the resolution to capture the motion of individual atoms. You sort of smear over their motion and then ascribe a gross continuum displacement field, and you get the theory of conventional elasticity. So this is really the root of a lot of mechanical engineering, so to say. So this is what happens for a very simple material. If you had a more complicated material where there's three dimensions, there is anisotropy, there are atoms that are connected to each other through bonds of varying stiffness. Let's say, for example, carbon, where all the atoms are similar, but then there's a lot of anisotropy that comes in. You can again go and compute what the band diagram is, so the phonon dispersion relations. And instead of two kinds of bands, you'll actually get multiple kinds of bands that describe all sorts of various anisotropic motions that can exist in this material. And this, in the 70s and 80s, this was a whole industry of people trying to calculate these things, measure them using X-ray diffraction, neutron scattering experiments, and then try to match up the two, and they actually do match up. So, these things are very well understood. So vibrations are phonons. So what do I mean by that specifically is, if I take any branch of dispersion in a real material and take any point on there, so any point meaning any particular wave vector which then corresponds to a certain frequency, that can be considered to be a local harmonic oscillator, because it's a normal mode of some other harmonic oscillator. And if you have a harmonic oscillator, you have this a standard potential well that's quadratic as a function of position, and the quantum mechanics of that says that excitations in this potential will sit at discrete energy levels within the potential well. So you have the lowest energy state, which is the ground state, which quantum mechanically does not have zero energy. It's got certain half h nu of energy. Nu is the frequency of the mode, h is Planck's constant, and then every other mode sort of is harmonic with an energy gap of h nu, and you call this the lowest one the ground state, and this the first excited, and so on and so forth. I like to use this notation to describe them for the rest of the talk. So 0, 1, 2, 3, and so on. So what you see is that there is something very fundamentally different here compared to what continuum elasticity tells you. But I just said that continuum elasticity describes essentially the same thing, but with not with the same kind of resolution, so to speak, in the description. So why does this discrepancy happen, and why do we not really see it, or why do we even believe that this strange discrete spectrum of phonons exists? Well, it's because there are classical experiments that still are sensitive to gross aspects of this phonon description. So, for example, the classic example is the heat conductivity, the heat capacity of amorphous materials. There's a theory of Debye and Einstein that takes into account the distribution of phonons in thermal equilibrium, and you really get this low temperature T cube law that's characteristic of phonons in a material, in a gross material. And then there's thermal conductivity. Again, similar kind of calculation. You get thermal conductivity at low temperature that goes as T squared for a large number of materials. So it's almost a universal property. The same for the heat capacity. An even more exotic example is actually superconductivity, which some people don't really realize. It actually relies crucially on phonons existing in the material, because in superconductivity, the idea is that two electrons sort of pair up to create a Cooper pair. The Cooper pair then flows in the material without any resistance. So how does that happen? Electrons don't really like to pair up, because you think Coulomb interaction would repel them, so there's no reason to pair them up. The secret sauce that makes this happen in a superconductor is actually phonons. So electrons actually exchange phonons between each other, which then mediates an additional force, if you want to put it that way, which actually overcomes the Coulomb interaction, and that's how these electrons actually hybridize. Even at the nanoscale, you have heat transport effects that are fundamentally described by how these phonons propagate. So, for example, this is this famous experiment where Keith Schwab and Michael Rukas sort of measured the quantum of heat conductance in a material. So all these things work, all these properties, sort of gross macroscopic properties, sort of rely on collective effects of phonon modes. So there's none of these effects are directly sensitive to individual phonons, individual phonon excitations, or even individual phonon modes. So really, these are collective. You can calculate all of them as integrals over collections of modes and mode densities and populations in some thermal equilibrium. So these are all properties that still call for a discrete phonon level, but they're not sensitive to it in any experimental sense. So the question becomes, can you really observe these individual phonon modes, individual phonon excitations in a single mode? So, which means, let's say the first excited mode, for example, that be a single excitation of this particular phonon mode. Can you actually measure or control these individual phonons? That's the obvious question here. So the reason why this doesn't happen is, of course, most materials are in thermal equilibrium, which means that if you look at the typical probability of occupation of these different levels in a given mode, they basically follow, as expected in thermal equilibrium, Boltzmann law, where KT is just the thermal energy, K Boltzmann constant, T temperature, and then if you draw the phonon number distribution, all of them if the thermal energy is larger than the energy of a single quantum, all of the levels are essentially equally occupied. This is basically what gives rise to classical statistical mechanics, right? So that's almost like a canonical ensemble. But if you have a situation where the thermal energy is significantly smaller than the energy of a single quantum, then you can be in the ground state, and then with a very slight probability perhaps in the first excited state. But note even here that the ground state probability is far, far, far higher than the first excited state probability. And if you look at it carefully, the ground state just looks like a Gaussian distribution in space. So it's really nothing quantum mechanical about it. It's just that the size of the Gaussian is determined by some Planck's constant and so on. But if you look at the first excited state, there's something very funky going on. This is the, if you take the square of this shape, that gives you the probability of finding a phonon in position. If you take the square of this, you'll actually get a two-lobe distribution. So there'll be one lobe here that comes from the square of the thing here that gets flipped over when you take a square, and then there's a second lobe here. So that would mean that in the first excited state, the phonon actually can exist quintessentially quantum mechanically in two places at once, kind of a quintessential quantum mechanical effect. But again, at thermal equilibrium, you don't see that because the ground state is occupied by a large, dominantly occupied. And if you look at, our old picture of an acoustic and optical phonon, the acoustic phonon, because of low frequency, always exists, typically exists in this regime, in this hot regime, whereas the optical phonons exist in this cold regime, but in its ground state at room temperature, let's say. So how do you control or observe these two modes of motion? Well, think of how the dispersion relation of light passing through this material might. Light, if it's the wavelength of light is longer than the typical lattice spacing, it just propagates as a wave. You don't need to think of the particle character. So light just has a linear dispersion relation, omega c times k. And if you want energy conservation, you really see that light only couples to the optical phonon branch at these 2 points. And in fact, the slope of the light line is significantly exaggerated here, because the slope basically gives you the speed of light. The speed of light is about 1,000,000 times larger than the speed of a typical sound wave in a material. So this is quite, narrow. So which means that, you'll have Raman scattering near this k equals 0 optical phonon branch. And of course, Raman scattering is a very well-known effect. A typical example of this that's used in diagnostics is this thing called coherent anti-Stokes Raman spectroscopy. What that involves, at least the description as it's usually mentioned in textbooks and review articles, is you've got a beam of light that excites one of these phonon modes into some virtual state. That's what happens in Raman scattering. So there's some intermediate energy state that the excitation can go into and survive there because of the uncertainty principle. And then you send a second beam of light that actually stimulates the emission of this mode back, and you come back to some slightly higher vibration level. And you can do experiments where you use two lasers shifted by a frequency to probe all these effects. And this is something that's been done 30, 40 years ago. You see that the optical phonon actually decays pretty fast, a picosecond time scale sort of decay. But of course, this does not resolve the quantum state of a phonon. This is a purely classical process. Although you can draw these energy level diagrams, this is a purely classical process in the sense that the number of photons that's involved in the process is extremely large. So you have a classical description for that. You create a gross excitation of all the phonon modes in an indiscriminate fashion. There's no energy resolution, there's no frequency resolution, there's no time. There is time resolution, but there's no energy resolution, frequency resolution or momentum resolution to identify single phonon modes, or let alone single phonon excitations. So that's what people in Raman scattering do, a classical process. The other thing that people have done to try to control phonons at the quantum level is to actually modify the dispersion relation of photons by storing them in a cavity. You get this quadratic potential because in a cavity photons behave like a harmonic oscillator. So energy sloshes back and forth between the magnetic field and the electric field, and you have this, it's almost like the photons have a slight mass. And then, of course, you can couple to these acoustic phonons. And the typical way people do this is very simple. Your acoustic phonon in this case is just elastic vibrations of some spring on which there's a mirror attached, and then there's another mirror that forms a cavity, and then phonons and photons obviously talk to each other by the radiation pressure force that acts between the two. So this entire thing is what the field of cavity optical mechanics constitutes, and people have studied, phonons in the kilohertz regime, the megahertz regime, and gigahertz regime, and largely over the past 4 or 5 years, been able to achieve single quantum state control, or at least beginning to achieve single quantum state control of these acoustic kind of phonons. But you'll realize the way people do this is, if you look at acoustic phonons, they have because of the low frequency, they have very large thermal excitation numbers at room temperature. So the way people do this is they take room temperature acoustic oscillators, cryogenically cool them down to close to 1 Kelvin. It's the kind of thing that I used to do as a PhD student, and then couple them to pristine optical cavities, and then do the single photon, single quantum resolution kind of experiments. So the thing is, although they have their saving grace is, although they have large phonon occupations, their phonon lifetimes, especially if you cryogenically cool them, can be reasonably long enough that you can measure them easily with modern lasers and that sort of thing. The thing about optical phonons, on the other hand, is that they're complementary. So they exist essentially in their ground state at room temperature, but their phonon lifetimes are extremely small, and it's really hard to get single phonon control over them. And there's other extreme where all properties are good in a sense. These are the folks in atomic physics who study trapped atoms, and they're very low phonon occupancy. They've good phonon lifetimes. And we won't talk about them. And just for completeness, and of course, in this regime, we don't want to be everything is bad. There's no saving grace there, and nobody works there as far as I know. Okay, so that's the problem with optical phonons. They're good in a certain things, but you don't have any way to measure them, control them at the single quantum level. So a typical example of an optical phonon that one we work with is optical phonons in diamond. Diamond is a nice material. The optical phonon branch has typically exists in the 40 terahertz regime, which means that at room temperature, your thermal energy compared to the energy of a single quantum is significantly less than 1%, which means most of the population exists in its ground state. Now, how do we actually measure or control this? Well, let's think of how these things interact with light. So one way that the optical phonon, the phonon in the diamond interacts with light is again by Raman scattering. So what happens is, your laser light comes in, it excites a phonon, but then it also excites a photon simultaneously. That's called Stokes scattering. So to write that, I would say, I start initially with 0 Stokes photons, and the mechanical oscillator here, the phonon in the ground state, so that's also 0. And then after this Stokes scattering has happened, there's 1 Stokes photon and 1 quantum of mechanical excitation, 1 phonon. And the reason energy is conserved in this peculiar process is because the Stokes photon is actually downshifted in frequency. So the frequency difference of the mechanical oscillator has been taken from the Stokes photon, so overall energy is conserved. Another process that happens is the inverse of that, which is that if there is an excited phonon, it can spontaneously or in a stimulated fashion decay to create an anti-Stokes photon and nothing in the mechanical oscillator. So the mechanical oscillator basically decays from its excited state to the ground state at the expense of creating an anti-Stokes photon. In some sense, it actually, what it does is it actually takes this mechanical quantum and converts that to an optical quantum, and then there's no more mechanical quantum. That's what happens. So if you, and again, energy is conserved because there's a frequency difference here, and so on. So if you think about this process carefully, you would think that this looks like you're able to write a single quantum of a phonon, right? You send your laser and you've excited a single quantum of phonon, and then there's a Stokes photon that comes out. And it's important that the Stokes photon comes out. We'll come back to that later. And then there's this operation that looks like you're able to read out a phonon, right? You've got a single phonon that's excited, and you convert that to a single photon, which you can potentially measure. So that's great. You've got the basic ingredients for doing this, except now you have to do all this in a time resolved, frequency resolved, and mode resolved fashion, and then you would have the toolbox to do what you want it to do. What are the challenges of doing this? Well, the phonons have short coherence time, as I mentioned, tens to hundreds of picoseconds. There are continuum of phonon modes, so you need to get access to the single phonon mode that you care about. And the Raman cross section is extremely small. So the scattering probability of a single photon is something like 10 to the minus 21. So if you send 10 to the 21 photons, your laser photons, you would see probably one Raman scattering event happen. So that's pretty small. So how do we overcome all that? Well, we use a femtosecond laser to deal with the fact that to resolve this short coherence time, and the way to get around this low scattering probability is to actually focus down the laser to a very small volume in the diamond, so that you address this very small optical volume of phonon mode with a large number of photons, with a large photon flux, and then we can actually show that the scattering probability, because of this tight focusing down to addressing something like 100 billion atoms, gives you something like a scattering probability of 10 to the minus 10. It's still pretty small, but 10 orders of magnitude better than what you started out with. So you need high numerical aperture lenses to collect these and so on. So you need to experiment needs to be pretty compact to make this happen. And then how do you get a resolution of just a single mode? Well, if you think about it, if a photon scatters from a phonon, you need to satisfy energy conservation, but you also need to satisfy momentum conservation. What momentum conservation tells you is that the scattered phonon and the Stokes photon that comes out of the scattered event would have to have a slightly different direction compared to the excitation of the phonon and the excitation laser that you used. So now if you use a carefully placed single mode fiber to collect Stokes photon coming in a very specific direction, you've now isolated Stokes photons that come from a single momentum Raman phonon. So that's how we satisfy all these criteria. But there's one more ingredient that one has to have to do the single photon control, and let me try to explain how we combine all these things. This idea of how to combine this write operation and the read operation to do the thing that we want to do. So let's say you're at t equals 0, at time t equal to 0, your phonon starts in this thermal state. And what you then do is you send you do your write operation. So send a laser pulse, femtosecond laser pulse, you get your Stokes photon out. As I said, exceptionally, with essentially probability 1, nothing happens. Nothing. I mean, that's the meaning of saying that the scattering probability is 10 to the minus 10. Essentially, nothing happens. Everything still remains in its ground state. But with a very small probability, square root of 10 to the minus 10, the Stokes process happens. So you create this phonon and a Stokes photon, and with the square of that probability, you create the second order process, 2 Stokes photons and 2 phonons. But now you know that you've created a Stokes photon when this process happens. So now what you do is, if you come with a single photon detector that can actually measure the absence or presence of a single Stokes photon, which in the frequency domain means that you band pass filter this light and pass it to a single photon detector. If this single photon detector clicks, then you know that in fact this no event has not happened. So in fact, with a very large probability that you've actually created this particular state, the state that you want. And it's heralded by the fact that you detect the single Stokes photon. So okay, so now if you detected that, then with high probability that you've just created this state, but that's just the mechanical Fock state 1. So that's the mechanical state, this non-classical quantum state of motion with just a single phonon excitation in it. Now you let this state evolve, do what it wants to do for a variable time that I set, and then come with a second laser pulse because you want to verify the fact that you've actually created this state. So you come with the second laser pulse, copy this excitation into this anti-Stokes photon using this read operation. And then what happens is, so there's no anti-Stokes photon to begin with. There's this mechanical oscillator mode sitting in the state 1. And what this read operation does is essentially does a copy of the mechanical excitation into the anti-Stokes photon. So you get an anti-Stokes photon that's a copy of your mechanical oscillator, if this first operation had actually succeeded. So you've taken this one phonon that you've created and copied it to a single photon. Well, how do you verify that you've got a single photon and not some, not 2 photons or 3 photons or n photons? Because all of these other number of photons would exist if instead of creating a single phonon, you've created additional higher number of phonons. So the way to do that is use a property of photons in quantum optics, which is that if you send photons into a partially silvered mirror, photons don't actually split into 2. They either come out on one side or come out on the other side. Either they get transmitted or they get reflected. It's not that they'll just split into 2 and come out on both arms. So if you now put 2 single photon detectors on either output arm of this beam splitter, if it's a single photon, you know that either the first detector clicks or the second detector clicks, because a photon cannot split, or the reverse happens, that this detector clicks and that detector doesn't, which means the clicks have to be perfectly anti-correlated if it's a single photon. So if the clicks are perfectly anti-correlated, then you've got a single photon. But if you then know that fact, then as I said, we know from the physics of Raman scattering that you must have created a single phonon Fock state. So all these events have to happen for this to work out. So the experiment essentially looks like this. I won't spend much time, just to say that there's a CW laser that pumps a mode-locked dipsapphire laser that creates these read and write pulses, which then gets doubled in a OPO. So you get 2 different wavelengths of read and write, which you can spectrally separate and filter out easily. You've got a delay stage to let this free evolution of the phonon happen. Everything gets focused down into the sample, and then coupled into the single mode fiber to choose this particular momentum phonon that you're interested in, and then there are other filters to filter out the anti-Stokes and Stokes. And really, the interest is in the measurement here, how the measurement setup actually works, because there's a lot of filtering that has to happen to make sure that nothing gets contaminated in the measurement. So First of all, there are tunable interference filters that filter out both the read and write pulses, which are just classical, big laser pulses that have got a large number of photons in it. You don't want them to fall on your single photon detectors and saturate them, so you filter that out. And then you use dichroic beam splitters to split out the Stokes photon and the anti-Stokes photon. And then independently, they can be directed to single photon detectors, which is then connected to high-speed coincidence counters that can do all these, correlation measurements, or at least allow you to do that in post-processing by stamping them with time. Okay, so you want to first verify that your mechanical oscillator is in a thermal state, which means that you don't want to herald on this detection of a Stokes photon. You don't want to wait for these things to click and then do something else. You simply want to measure what the Stokes photon counts look like. You basically measure the correlation of the Stokes photon and another Stokes photon. In fact, if the oscillator is thermal, it doesn't give you a single photon that comes out. It actually gives you multiple photons. So both these things should be exhibited clicks, and in fact that's what you see. You see that there's a sharp increase in the click correlation at 0 time delay, which is just to say that if there are lots of photons that come here at the beam splitter, some of them will go here, some of them will go there. So with 0 time delay, if all these lengths are matched, you'll get simultaneous clicks on both. So in quantum optics, we call this correlation function as G2. It's just what I said, that you look at the correlated counts at 0 delay between two photon detectors. So indeed, you see that the mechanical oscillator is in thermal equilibrium. Same thing exists for the anti-Stokes, that if you go with a Stokes photon, excite it, but then don't care about what the Stokes process happened, and then look at all the anti-Stokes photons that come out. Again, there's nothing to actually filter out or post-select out those events where only the single phonon excitation happened. You just see the average of all these events and excitation events and non-excitation events that happen. Again, you see a thermal distribution. In fact, you should actually get, for a perfect thermal distribution and this correlation function value of 2, we don't actually get that because because of signal noise issues in our experiment. But the really crucial thing is that we can use this to verify that we are simply addressing a single phonon mode, because we have a model that says that, in fact, if n phonon modes participate, this G2 function should go as 1 + 1 over n, which means that if n is 2, for example, this should be 1.5. So having this correlation above 1.5, in our case 1.75, already tells us that we are able to address a single phonon mode, and that's really important. Okay, so now we've done this experiment where we look at individual correlations of the Stokes photons, individual correlations of the anti-Stokes photons, which tells us that the phonon exists in its thermal state if you don't do all this post-selection experiment. But now you can ask a different question, which is, what is the correlation between a Stokes photon that is emitted after a write operation and the anti-Stokes photon that is emitted at the subsequent read operation after a certain time delay? They should be correlated because they are mediated by this phonon that was excited in the write operation and that was stimulated back during the read operation. So we study that. And of course, if you think of the probability of clicks of these two detectors as two classical random variables, that from classical probability that correlation functions have to satisfy a Cauchy-Schwarz inequality, which means that the Stokes anti-Stokes correlation should be less than the square root of the Stokes autocorrelation and the anti-Stokes autocorrelation, and the value of that, if you evaluate this by classical physics, should be 2. Okay, so this is what classical physics should predict, that these correlation functions should satisfy this Cauchy-Schwarz inequality. But if you actually make the measurement, you see that something dramatic happens, which is that this anti-correlation function at 0 time delay actually violates this inequality by a large amount. In fact, it violates it by several orders of magnitude. In fact, if you look at the statistics of this, the error bars on these are actually smaller than the size of these points. So it violates this by several tens of standard deviations. So it's extremely surprising, right? Because this seems to be a very general statement about probability distributions and correlation functions. So what is going wrong here is that you're really seeing something that's quintessentially quantum mechanical, which is the fallacy in applying this classical logic to this experiment is that you assume that there is in fact a joint probability distribution that describes the joint events of these two detectors, and that does not exist in quantum mechanics. So that's the crazy thing about quantum mechanics. Even though individual measurement outcomes in quantum mechanics are random, there may not exist joint probability distributions to describe two different measurements. And that's crazy. That is in fact something fundamentally quantum mechanical, and that's precisely what we see here. So the joint state cannot be described by some classical probability distribution. So we'd like to understand what this joint state is. And as I said before, this joint state would be some state involving the Stokes photon, the anti-Stokes photon, and this single quantum excitation of this phonon. And we'd like to see that. So the way to see that is do precisely what I mentioned to you before, which is do this experiment where you wait for this Stokes photon to trigger, telling you that you created this single photon excitation once in a while, and then do this try to see if the anti-correlation of the single anti-Stokes photons that come out here are indeed anti-correlated. So this ideally, if that clicks, if the Stokes detector clicks, then you should have projected your thermal state into a Fock state. And there's a technical terminology for this. Thermal states are called bunched. They have this G2 of 2, which I showed before, and Fock states are so-called anti-bunch states, extremely non-classical states. They've got a G2 of 0, in fact, perfectly anti-correlated. In fact, if you this bunching statistics of these two photon detectors conditioned on this guy clicking, you actually see that at time t equal to 0, you actually do see extremely high anti-bunching. The reason it doesn't go to 0 is because there are dark counts in the detector. They get accidentally dark counts in one detector and dark counts in the other detector get accidentally correlated, and we don't actually have the resolution to eliminate those events. Nevertheless, it actually is significantly anti-bunched compared to this classical bound of 2. And in fact, if you track the depth of this anti-bunching as a function of the delay of the right-hand read pulse, you actually see that this phonon Fock state that was actually very non-classical at this point sort of slowly decays back into a thermal state and again goes back to being bunched. In fact, similar experiments have been done in cavity optomechanics a couple of years ago at 35 milli-Kelvin temperature in an optical cavity in a dilution fridge, and people had measured an anti-bunching of something like 0.6. We actually do this at room temperature, no cavity on a piece of diamond. In principle, the entire technique is agnostic to even the fact that it's diamond. You can do it on arbitrarily other materials that exhibit any kind of Raman activity, which is plenty of materials out there. And we see anti-bunching of 0.1. And really, this plot shows you, the birth of a single quantum of excitation here, where you see it's perfectly anti-bunched, and its slow death from a quantum state back into a classical thermal equilibrium here, where again it goes back to being bunched, which of course is the case here before, well before the second pulse came along to do this. So if you run the numbers, you would see that this experiment actually creates a phonon Fock state with about 98.5% fidelity. So yeah, so that's basically what I wanted to talk to you about. I'm open to questions at this point, essentially because I've run out of time. But we've been able to, extrapolate this technique to do even crazier things, which is cooler things, I would say, which is, instead of studying the quantum state of a single phonon that we create, we can actually study the joint entangled quantum state of a phonon and an emitted photon, and we actually show that this entanglement satisfies something called or violates something called the Bell inequality, which is to say that the kind of entanglement that we see is something that cannot be explained by any classical probability distribution or anything like that. So it's a true proof that we've created something fundamentally non-classical, even across a photon and a phonon. And with that, I'll stop. The interested audience can talk to me about that. Thanks.
Vivishek, thank you. I send you the virtual and the physical, the real clap here. So thank you very much for the fascinating talk. Participants, please enter your questions in the Q&A or the chat. Let me get going with sort of something to launch us off with. Vivishek, what are the applications that you're most excited by that will be enabled by the ability to do this type of interrogation?
Right. So we are actually at a point where you can take essentially any mundane material that you can get your hands on that has a Raman scattered cross section and study single phonon dynamics in it. Well, why is that important? You go back to this first slide that I showed, where there's these other classical applications of what phonons do in materials, heat conductivity, heat transport, superconductivity, and all that. I mean, there's something that you can think that there are exotic materials out there, exotic superconductors perhaps, where single phonons and single phonon excitations probably can control them maybe switch heat conductivity or heat transport properties by controlling single phonons one by one. So these sorts of things, right? So these are applications, potential applications. Of course, I'm going off the rail here, trying to speculate how these might be applied. But these are the kind of things that that I can reliably speculate about. There are also speculations about phonons might have something to do in biology and these sorts of things. But these are very speculative.
Very good, thank you. So a question here from David Bowen. Do you have to worry much about vibration isolation from the environment when you do these measurements?
Yep, to a certain extent, yes. So really, vibration isolation becomes very, in some sense, important and some sense not important. It's not important in the sense that the phonon that we care about is a 40 terahertz phonon. So nothing in the world, in the lab, typically vibrates at 40 terahertz. That's a very high frequency, right? So the optical table is not vibrating at 40 terahertz, nothing of that sort. But the way we care about this is the measurement apparatus does care about this, because a lot of our calibration, the delay of the write and read pulses, it's just spatial delay. These are actually calibrated to certain lengths, and they need to be calibrated out, and vibration does play a role in the calibration of this experiment. For the Bell experiment, vibrations play a very huge role, and in fact, we've come up with a clever technique to engineer an interferometer that's actually vibration sensitive to do that.
Thank you. So the question that was chatted here directly, if I understand it, it's asking about the feasibility of miniaturizing some of the measurement techniques through integrated photonics.
Yep.
For example, how do you take it from a lab bench demonstration to something that's actually a sensor on a chip?
It's not infeasible to do that. What do we need? Well, we need a femtosecond laser and an OPO to drive this experiment. That's kind of hard to miniaturize, but I don't think people maybe care about miniaturizing that. But at least on the detection side, where you need to have this three single photon detectors, one waiting for the anti-Stokes photon to come, and two waiting for one for the Stokes photon to come and herald the process, and two looking for this anti-correlation. That potentially can be built on a chip, and people are actually successfully integrating single photon detectors on a chip. Maybe not with the kind of efficiencies that we have. What that means is that you'll have to wait longer to take this kind of data. In principle, possible. In practice, at this point, only limited by technology.
Very good, thank you. Participants, if you have any remaining questions, please, now's your chance to either put them in the Q&A or chat. Give you a few moments there. Okay, so I think with that, Vivishek, thank you. I look forward to reading more and learning more about your work, and thank you for sharing your time today. And participants, thank you for joining us. As you know, this is our weekly way to stay connected and excited by the work that's happening in the department, by our students, by our faculty, by our partners. Next week, same time, same channel, Wednesday at 12 noon, July 15th, we'll hear from Dr. Calvin Kausari. He'll be talking about scalable visible light additive biofabrication. And I hope that you can join us again next week. Vivishek, thank you for, again, your time and your phenomenal work.
Thank you.
Participants, have a good day and stay safe. And, oh yes, thank you for the reminder, Teresa. If you would like to self-nominate yourself or others and to be able to share about the work that you're doing, about the work that you're doing in the lab, or the work that your industry partners are doing, or companies that you're interested in, please do drop us a line. It's our way to stay engaged and to build and foster the MechE community. So thank you, and everybody have a good day and stay safe.
Thank you, Professor Sudhir. Have a good day.
Thanks, Brian. Thanks, Teresa, and
Thank
thanks
you.
everybody for tuning in.